Welcome back to our first hands-on video for writing the MNIST classifier from scratch. In this video, we're going to take care of importing the packages and also defining the model class. So for importing the packages, obviously, I'm going to import Torch, which is the Pytorch package. Then I'm going to import torch.nn submodule as nn. Next, I'm going to import torch vision.datasets as datasets. This is the repository where the MNIST data is located, and we're going to use it for downloading the MNIST dataset. Next, we're going to use import torch.optim. We're going to need this part of the Pytorch in order to use the optimization functions that are already stored in torch.optim submodule. And from torch.utils.data, we're going to import data loader. Data loader is a very important and useful utility function which allows us to take mini batches of the data and pass it to our model, both for training and also test purposes. So I'm going to run this cell. It works. All the necessary packages are imported at this point. Now we're going to write the codes for defining the model class. No matter what kind of model we're using, we always define a class for our model. And in this case, I'm going to define the class by obviously assigning a name to it. This is my image classifier. And I'm going to inherit from nn.module. This is a class, so obviously the first method to introduce is the init method. And I'm going to leave some placeholder for the inputs of the class. The first thing right after init to write is the use of the super function, which allows us to inherit from nn module whatever characteristics that nn module init method has. We're going to inherit it for our image classifier. So super my image classifier and self dot init. That will do it. Now we're going to define the body of the model. Self dot, I'm going to name it my image classifier using the underscores. And now I'm going to use nn sequential. Sequential is a very handy tool under nn module which allows us to stack various layers, various neural network layers to each other. So it basically connects these various layers to each other, making the model for us. Now here I'm going to use a model. For our fully connected layer model, I'm not going to make it a very complicated model. We're going to use a very simple model. No hidden layers. We're going to just have one input layer and one output layer. So nn.linear for the input layer, we need the number of input features and the number of outputs. So the number of input features for the very first layer is definitely the number of pixels. So I would say num pixels. And then for the output, I'm going to say num out from layer 1. Then obviously this layer requires a nonlinear activation function, and I'm going to use relu. Don't forget to use this. And then I'm going to use the final layer, write the final layer, which is again, and in the linear, the inputs is equal to the output of the previous layer. So num out, oops, 1. And then the number of outputs from the last layer is most likely equal to the number of classes. So num classes. And I believe it's 10 number of classes in the MNIST dataset. So we defined the body of the model, but we need to introduce a new method which runs any input images into this model. So we historically and conventionally we call it a forward method. Forward method receive x. Let's say x is the mini batch of data or images. And then we say x is equal to self dot my image classifier of x. So x gets run into that model that we wrote, and then for purposes of saving memory, we store it again in the same memory slot as x was, and then we return it. So here we're done by writing our model class. I will run it. There's no writing error in it, but most of the times when you write a model class, we can immediately test the model by seeing whether the input data, a randomly generated input data with some known dimensions, will pass. If we pass it through the model, it will give the expected dimensions as the output. And then that means that our model is most likely written correctly. So what we will do here is that I'm going to instantiate our model. And now I need to do something that we kind of forgot to do. We need to see what kind of inputs we want the model have. Obviously, number of pixels, number of out features from model layer 1, and number of classes are the inputs. So here I'm gonna arbitrarily choose some numbers. 500 as the number of pixels, 50 as the number of output features from layer 1, and 10 as the number of classes. After doing that, I'm going to generate some random images, and for that I'm going to use torch.randn. Let's say we have a mini batch of 35 images. They have one layer each, and they are 25 by 20 pixels. And 25 times 20 gives us a 500 pixels per image, which is equal to this number here. So these definitely need to be equal, otherwise we will get an error. Obviously, we're not using a convolutional neural network, so the first thing to do is to flatten the images. So x is going to be x.reshape of -1 and 500. And now y as the output of the model is going to be model x. So we pass x through the model, and whatever is the output is going to be y. Now I'm going to print y.shape. And our expectation is to get definitely 35 by, instead of 500, we will get 35 by number of classes, which is the output. So 35 by 10 should be the output. There's an error. Oh, yes. So whatever change we made to our model after adding the inputs here, we didn't run it. So we need to run it so that the model knows there's some outputs, and then you will see that torch.size 35 by 10 is the output that we wanted. So we're good to go. The model works. We imported the packages we needed, and we wrote the model. I will see you in the next video where we're going to download the MNIST data and define a data loader. And we're also going to think about some hyperparameters for our model. We're going to define the device. We're going to write the codes for the model, optimizer, and loss function. I see you there.